We're going to start in a few moments our next section. There's only two during this quarter, this week, but they're long and big. First one's going to be the chain rule, which of all the rules that you're going to learn to how to find derivatives of functions, this one is going to be the most versatile. Because what the chain rule allows us to do is to find derivatives of functions that would be impossible any other way, and to find derivatives of unusual combinations of functions. And this method is called the chain rule. It's not like the product and the quotient rule where there's a formula like f dash g plus f of g dash. Technically, there is a formula for it, but no one ever uses it because it's not that useful. The chain rule is much more like a process. So you have to think of it as a process, a way to do something, right? Analogy. Do you know, like multiplying a 3-digit number by a 4-digit number could be written down as a whole load of steps, but don't you really do it as a combined process because there's so many different combinations of numbers and things that can happen that you have to basically know how to do the process rather than, you know, the details that make it up. And so we're going to be looking at this thing, this new rule called the chain rule, and we're going to do it with powers, right, with square roots and cube roots, with things like 5 over something cubed, e to the power of something, or 2 to the power of something, sines, cosines, things like that. And then we're going to use it along with the other two rules that we use, the product and quotient rule. And then we're going to finish on applications, which for the most part will be find equation of tangent lines or find the derivative so that you can get velocity and or acceleration. And also today, hopefully if I remember, if I forget, we'll do it tomorrow. Also today, we are going to be looking at some information about your midterm, because as you know, that's going to happen a week today, and that is a biggie. So let's look at the chain rule. And the first thing we're going to deal with is how you can use the chain rule with powers. So imagine I have a function. That function. Now, if you had to differentiate it with the techniques that you know, I guess you could write it down as 100 5x squares plus 2x plus 1s all multiplied together, and then create some evil version of the product rule with 100 pieces to it, and then do it. Now, if you think about that, wouldn't that be just impossible to do practically? It just wouldn't be on the plate. Well, you could FOIL the thing out and then just differentiate the biggest polynomial you've ever seen in your life, because that polynomial would have something like over 100 terms in it. Probably take you over 100 hours to do it, but theoretically, at least you could do it that way. Would you also agree that it's a pretty dumb way of doing it? Nobody wants to do it that way. So you can imagine the first mathematician who came up with this, and he thought, oh God, the only ways I know how to do it are not ways I'm going to do it, right? There must be some other method. And they come up with this idea of the chain rule. In 141, you talk about composition of functions, or functions of functions. And that's where the clue to how to differentiate this thing comes from. This guy here inside the brackets, this guy here is going to be called the inside function. So you'll hear me use that word or term a lot, the inside function. And here is the trick. This is the process. Cover that thing up so that it doesn't look like an expression anymore, and just say the inside function to the power of 100. In fact, just say something to the power of 100. Just like x to the power of 100 or b to the power of 100. And you can differentiate the inside function to the power of 100 because it's 100, the inside function, to the power of 99. Now, if that's all the chain rule was, wouldn't that be a very simple rule? But you have to finish with times the derivative of the inside function. So it's going to be 100, the inside function to 1 less power, times the derivative of the inside function, which in this case is 10x plus 2. Kind of sneaky. Then tidy it up. Not a lot I can do, but I could pull out a 2 from here and get 200. If I pull out a 2 from here, I get 5x plus 1. And then I have this guy. We're finished. The derivative of this function is 200 times 5x plus 1 times this thing to the power of 99. Now, if you compare it against the two methods I talked about, horrendously big product rule, or horrendously big FOIL everything out, then differentiate, would you agree that this method wins hands down? It's just 100 times more efficient, and it's good. But it is a process, isn't it? You have to kind of recognize the inside function and recognize this as something to 100. Then you get 100, something's to 99, and then just finish with the derivative of the inside function. And that lies just tidying up. Okay, let's try another one. Five x plus 3 to the power of 1,000. 1,000 times the inverse the inside function to 999 times the derivative of the inside function, and then make it all look pretty. I'm always amazed at the intelligence of people 400 years ago to come up with this, how they figured it out. But once they figured it out, isn't it nice for the rest of us? Because we just need to know how to do it, not how the heck did they figure out that that worked. Oh, and as an added bonus, don't you get quite nice style points out of this method? Right, you get to have all sorts of combinations at work. So let's try one last one of this type. Okay, I'll take a volunteer. Anybody feel that they're comfortable with this method enough to tell me what the answer should be?
Sure. So
Okay.
I guess we'd start off as 12 times the inside function to the 11th power times 15x squared minus 2.
Perfect. I'll do the next bit for you. I'm just rearranging the furniture. Typically, when you write expressions that are big, long expressions, the rule is simplest to ugliest. So numbers, smaller expressions, big expressions. And that's typically the order you write. So if I gave you a guy that looked like this one here, do you all feel comfortable you could use the chain rule to differentiate it? Okay, so let's cross that off our list of things that the chain rule can be used on. Okay, let's do the chain rule with radicals, right? Square roots and cube roots. So how about y equals the square root of 5x squared plus 2x plus 1. And so how does this chain rule process work this time? Well, if I was just doing the square root of x, I would rewrite it as a power of half and do that with all radicals. So if it's a cube root, make it a fractional power, right? Make it 1/3, right? If it's a square root, make it 1/2 power. Now in this question, can you all see the inside function? You recognize this would be the inside function. So essentially, don't we have something to the power of half? So I can use the power rule, which is 1/2 the inside function, then reduce the power by 1, and then finish with the derivative of the inside function. So it's going to be 10x plus 2. And no, you are not finished. Style points. Make it look pretty. What do you think I'm going to do with this inside function to the power of -1/2? How am I going to rewrite this? Style point.
Put it in the denominator.
Agreed. You probably don't need this in particular line, but I'm going to put it in anyway. Now, we have a half and we have this. So can we just distribute that and get 5x plus 1? Are you all comfortable with that? 1/2 times 10x plus 2. Now, one of the 3 rules in style points is make me look like the original. Agreed? So when we're finished, this guy on the bottom will turn back into a square root. So we now know how to differentiate square root of almost anything. Agreed? Chain rule doesn't really care that that's an x squared. It's going to be an x cubed, or almost, as you'll find out later on, anything at all. Try another one. So I'm going to be differentiating 6 times the cube root of somebody. So I'll rearrange it as 6, 5x squared minus 1 to the 1/3 power. And the inside function is that guy. So we can now differentiate. Multiply by the power and reduce the inside function by 1, followed by the derivative of the inside function. Then some style points. Bring the negative power fella downstairs. And then return it back into its original form. So this 2/3 will become a cube root, and a cube root of 5x squared minus 1 all squared. Are we comfortable with that guy? Do you see that there isn't any formula? I'm not even writing that formula down. I might write it down, I don't know, at the end, just to show you, what the formula looks like, and then tell you you never use it. I might actually just, now I'm thinking about it, not even bother to tell you the formula, because I haven't used it yet and I never will. So I'm not sure telling you it helps. So now I've thought about it. If you want to know what the formula for the chain rule looks like, go look it up. And I'll tell you right now, it won't do you a darn bit of good because it isn't useful. You do it this way. You do it as a process. Let's try another one. I want to find the derivative of the square root of 4x squared plus 1 cubed. Okay, so the first job is to rewrite this guy in a form that's going to be differentiable. Okay, what fractional power of 4x squared plus 1 is this guy? What fractional power is this guy?
1/2.
Okay, and we would call it 3/2. Now we can differentiate. Remember, our inside function will be this guy. So it's going to be 3/2 the inside function to the power of 1/2. So multiply by the power, reduce it by 1, times the derivative of the inside function. And this, if you multiply them together, gets you 12x. Ooh, I almost made a mistake there, so I'll kind of write this down. So you get 12x and just the square root of 4x squared plus 1. I was about to make that a fraction, and it isn't a fraction. And there you go. Okay, last one. I'll take a volunteer who feels comfortable about rewriting that as a fractional form and then differentiating it for us.
Me.
Go for it.
So differentiable form, turn the 4 root to a fraction, so x cubed minus 1, 3/4.
Okay.
And then we want to do chain rule, so 3/4 times x cubed minus 1. And then it'd be like -1/4.
Yep.
And then the derivative of the inside, so it'd be 3x outside.
3x?
Yeah. Squared, sorry. Missed that.
Okay. Looking good? I'll finish it. You multiply these guys together, you get 9/4 x squared. This guy will go on the bottom. So you'll have 9x squared, bring that 4 downstairs, and put a 4th root of x cubed minus 1. Have you noticed it kind of sneaks up on you how ugly some of these derivatives that we're doing now are? I mean, the 4th root of x cubed minus 1 cubed, if you imagine 20 minutes ago, you would be looking at that if you didn't know about the chain rule and just say, can't do it, right? There's no way I could do that, right? But actually, it is doable. Pretty ugly answer, but it's doable. Okay, are we good with radicals, things with square roots and cube roots and so on? Last chance. Okay, cross it off our list. Rationals, fraction functions, essentially. I'm talking about fraction functions that look like that. A number on the top, but just a number, nothing else, right? Just a number on the top and some cube, square, whatever it might be on the bottom. That would count as a fraction, right? A rational function. How would I rewrite this function so it's differentiable? Because right now it's not in a differentiable form. How would I rewrite this in a differentiable form?
You move it to the top and make the cube the negative cube.
Agreed. You all remember doing that when we started 4 over x cubes, right? Call it a negative power. Now, the inside function is that guy, right? And the rules don't change. It's essentially a power rule, right? It's like 10 something to negative 3. So you multiply by the power, and then you reduce the power by 1. And then you finish with the derivative of the inside function. And then you do style points. These two guys go on the top. And this guy looks better on the bottom. It was quite clean, wasn't it? Wasn't too many weird stuff going on there. Okay, we'll try this fraction, this rational function. First, I'm going to write it in a differentiable form. So it becomes a negative 100 power. And then I can do essentially the power rule. So multiply by the power. Reduce the power by 1. And then multiply by the derivative of the inside function, which is 2. So we now have negative 800 2x minus 1, and I apologize for that line, but it was too late. I'd already written it. Really, you just go straight to this line, wouldn't you? And you'd be finished. So far, so good. Okay, let's put the cat amongst the pigeons. Let's do a fraction that has a square root in it. Now, you wouldn't typically do these lines, so I'm taking it slow. First thing I would do is turn the square root into half power. And since this square root is on the bottom, if I want it to be in its differentiable form, it needs to be written like that. Are you all comfortable about the original function now being transformed into this differentiable version of itself? You comfortable with the half power, and then because it's on the bottom, you now have a negative power? So far, so good. Right, let's differentiate then. Multiply by the power. And reduce the power by 1. Then finish with, oops, there's my little inside function. Then finish with the derivative of the inside function. And then you make it look pretty. Negative powers go on the bottom. Make it look like the original. So fractional powers become square roots. And the 3 makes that a cube. Does that seem still part of the process? Would you agree we're still following the rules of make it differentiable and then just do the inside functions, right? So multiply by the power, reduce the power by 1, finishing with the derivative of the inside function. And then put things together. Negative powers go on the bottom. And fractions get turned back into radicals. Looking good? Okay, no pressure. There's 3 questions. You get 3 minutes to do as many as you can. Go for it. Last few seconds. Okay, one of the reasons I give you these little things is that sometimes you don't know what you don't know until you try it. So you're nodding your head and you're thinking, yeah, I can do this. And then you actually go and try and do one, and then you suddenly realize that maybe you don't. So it's a good way of testing, do I understand it? So here goes. This one is good to go. Inside function is going to be this guy. So you do multiply by the power and reduce the power by 1. And then you finish with the derivative of the inside function. And you might or might not have noticed this, but it is important in style points. You can factor out a 10 here as a common factor. So what you actually get is 30 times 10, which is 300. Then you have an x minus 1. And then you have a 5x squared, take away 10 to the power of 29. So hopefully you cut up that little style point issue. Now, to be able to do this one, you have to rewrite it in a differentiable form. And now it's just multiply by the power, reduce the power by 1. Remember, this is the inside function. So you finish with the derivative of the inside function. And in this case, there really isn't too much to do as far as style points go. And that's the answer to that one. If you want to do,
question about number 1.
yes,
When you took the derivative of the inside function, shouldn't it just be 10x?
you're right. So
And also, when you took
now I
the-
fixed it by making that 10x.
no, on this one, this one you made it 6x cubed, but shouldn't it be 6x squared?
Yes. We good now?
Yeah, I was just want to make sure.
No, you're right. That's what I get for being too quick. I'm going to write this guy as 2/3, so I'll be a bit slower this time. The inside function this time is that guy. So multiply by the power, reduce the power by 1, and then you finish with the derivative of the inside function. And 2 lots of 2x minus 1 on the top. That 3 is on the bottom, and that becomes a cube root. And we are finished. So as long as we give you powers, fractions, or square roots, the chain rule seems to work well with all of those.
I have a question about number 1.
Yes.
Can I see it again? Thank you. In the second row, right after you multiply it by the power of 29, and you have the parentheses 10x minus 10.
Yeah.
I didn't derive it the same way. Did I mess something up?
No, you derived it the way the original question was written, which was minus 10.
Oh, okay. Okay, cool. Thank you.
I just changed the question to suit the answer because it was easier than fixing the answer. So you were right. So here we go. Exponentials. But they're going to be 2 kinds. They're going to be that guy and some other guy that I won't talk about quite yet. So let's look at e to the power of x squared plus 1. Now in these situations, that's your inside function. your inside function is mostly where an x would be if it was a simple version of itself. So if this would be e to the x, the place where the x is your inside function. So here it's e to the x squared plus 1. So its derivative is e to the power of the inside function times the derivative of the inside function. Does that seem reasonable? Are we still following the same process? Any questions about that? You still good? Okay, try another one. Suppose it was e to the power of x cubed plus 2x squared plus 5x plus 7. The inside function would be the power, right? All that stuff. And the derivative of e to the something is e to the something, e to the inside function, times the derivative of the inside function. Well, that guy's 3x squared, that's 4x, and that guy is a 5. And really, all you can do as far as style points go is you tend to start with the simplest, which in this case is that guy, and then finish with the ugly one. So here's a couple of baby ones that can throw people. I'm going to differentiate e to the 2x, and then I'm going to do e to the negative 2x. Well, the inside function here isn't much of a function, it's just 2x. So e to the e to 2x, because you e to the 2x, times what? What is the derivative of the inside function here?
2.
So do you see that the derivative of e to the 2x is just 2 times e to the 2x? In that same vein then, you should be able to tell me the answer to the other one without having the middle line. What would the derivative of e to the negative 2x be?
Negative 2 times e to the negative 2x.
In fact, won't e to the 10x be 10 e to the 10x? And e to a billion x is a billion e to the billion x. So, isn't differentiating versions of e to the x, at least when there's numbers, very easy? When they're powers, you know, like this, you have to do a chain rule. There's just too much going on. Although some people can do from there to there in their head, which is, I could probably use that one. They're all still the chain rule. Great. So who's this guy? Well, we have never differentiated yet bases, exponentials, where the base is not e. We call this the base, the thing that goes here. So this exponential, right, has a base of e. This one has a base of 5. So I'm going to have to show you before we even tackle this question, what the derivative of that guy is. And yes, he is that guy. But I'll put it in red to emphasize it. It's the natural log of 5 times 5 to the power of x. And that little extra piece, natural log of 5, happens because the base is not e. If the base was e, wouldn't this be the natural log of e times e to the power of x? But isn't the natural log of e 1, which makes that base so much special compared to any other base? Okay, so if you want to differentiate y equals a to the power of x, where a is any number you like, 5, 10, even e, its derivative is the natural log of a times a to the x. So don't forget that little natural log of a guy. We'll actually be able to prove this to you when we do logarithmic differentiation. But right now, you're just going to have to trust me that that's true. So we're now going to expand our derivatives that are exponentials from e to the x to any number to the x. In fact, any number to any power of x. In this function here, what is the inside function called? What is the inside function here?
X cubed plus X.
Agreed? You kind of have to know what the inside function is to do the general, don't you? Because isn't the last thing you end up doing is times the derivative of the inside function. So you have to kind of know who it is. So if you want to differentiate 5 to the power of something, you remember that extra log 5 bit. So that's that done. And then you finish with the derivative of the inside function. And then you kind of make it look pretty by just rearranging the furniture. That wasn't too bad, was it? How about this one? I want to differentiate 10 to the power of 2x minus 1. Okay, anybody want to have a shot at that? 10 to the power of 2x minus 1.
Would it be the natural log of 10 times 2 times 10 to the 2x minus 1?
Yeah, I'm just doing it in slightly different order, but you are correct. There you go. Okay, one last one. If I wanted to differentiate 2 to the power of x cubed minus x, you would get the natural log of 2, 2 to the power of x cubed minus x, right? So basically, natural log of 2, this guy again. Your inside function is this. So you finish with the derivative of the inside function. And then you kind of rearrange the furniture because of style points. So it looks good. And that's that guy done. Okay, if I gave you an exponential, do you feel comfortable you could find its derivative? Right, so an e to the x cubed or a 2 to the power of x cubed minus x, those kind of things. So you can't, it's not that you change the chain rule, but don't you have to adapt it to different circumstances, right? A 2x plus 1 to the 100 is not quite the same as 5 to the power of x cubed plus 100, right? They're different looking things and we have to adapt them. And hopefully that's what you got from that. Right, so what we're going to do now for the last few minutes is talk about your midterm. So here goes. Hopefully you're looking right now. Oh God, what's that window doing there? Are you looking at our Canvas page? Oh, good. Right, yeah, you see there's a new module called Midterm Exam, Monday, 7 a.m. to 9 a.m. That's there. Now, it's not completely filled in, but most of it is there right now. Here is a practice midterm for you with solutions. Here is instructions on how you're going to upload a program called Microsoft Lens. Basically, it allows you to take pictures of your working, because I'll be looking at your working, and converts it into things like a PDF, and that way you can upload it. And there's Desmos, because you know you're going to use Desmos in some questions just to see it. That is an empty one. It better be. Good. It's a placeholder, but on the day of the midterm, when you click on that, that's where you'll find your midterm. There'll be a PDF there and you'll be able to read the questions. Here is where you're going to upload your working, okay? So if you click on this, and you can do this, there's no damage in you doing what I'm doing. You can then hit Start Assignment, and then you can upload file, then you go choose file, and you choose a file. Hopefully you call it something that makes sense, and then you submit assignment. And that's it. That's how I get your working. So on your phone, you're going to have Microsoft Lens or whatever program you've used for other classes, I don't care, right? Take pictures of all your working, upload them into here, and that's it. Now, during the exam, there is going to be, although it's not here yet because I haven't made it, there's going to be a Zoom link, not the usual class Zoom link, but a midterm exam. And I'll put it in here and it'll say something like Zoom link to midterm. And that's the one you'll click at 7 a.m. So you're going to have an early rise next Monday, right? And you'll go in there and I'll be watching you. And there are some instructions about what you can and cannot do. But I've just looked at our time and I don't want to eat into your time. So tomorrow, I'll have a few more things on this and we'll talk a little bit more about it. But right now, I guess the important thing is it's Monday, 7 till 9. And you may want to go and download that guy there, right? So if you do a click on this, there's the link if you have an Android, there's the link if you have an Apple, and there's a little video that shows you how to use it, okay? And last name, and bye-bye.